All right, friends. The the pandemic has clearly taken its toll. This is now take 3 because I uploaded the last one with no sound. So fingers crossed, we now have sound. Hopefully this gets easier. All right, enzymes. We're talking 6-4 and enzymes. And when we're talking about enzymes, what we need to remember is that they're a subcategory of proteins. Now, why is this really important? So let's go ahead and let's take a look at this image here. This image is of an enzyme subgroup of proteins. Proteins, let's refresh. Proteins are made of amino acids. So the monomer of proteins are amino acids. What do we know about amino acids? Well, they're really, really cool and they're in a specific order. And if we recall, when we're talking about proteins, we're going to go from that polypeptide chain to the alpha helices and beta pleated sheets in the secondary structure, to the R groups of the proteins, that variable structure of the amino acid, folding into that tertiary 3-dimensional structure, which is what you're looking at here. That tertiary structure of any protein function. So the highly specific order of the amino acids directly relates to how the protein folds, and how the protein is shaped. All that folding dictates the function of the overall protein. So in this particular case, what you're seeing is this 3-dimensional shape, really uniquely folded, and all of that folding is due to the various R groups. What you should be able to see here is this little pocket. And with an enzyme specifically, usually you have an active site. And what that active site means is that that is where it's going to attract specific molecules that are either going to build up or break down corresponding molecules. So enzymes are catalysts, meaning they're facilitating a reaction happening. Those reactions typically are going to either be breaking things down or building things up. Why do we have enzymes? We have enzymes because if we allowed these reactions, which would normally occur, they're all spontaneous reactions, would absolutely normally occur, but they would occur at such a slow rate that we wouldn't be able to survive. So we need enzymes to facilitate these reactions at a much, 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 much faster rate. How do they do this? Well, they're pretty neat, and they're going to do this by lowering the amount of activation energy required for the reaction to take place. So if we zoom in on this diagram here, you have the rate of the time span of the reaction, and you have the amount of energy it takes. All reactions are going to take some initial activation energy. And why is that? It's because if you have molecules that are bonded together, they're relatively happy. You're going to need some energy input in order to break them apart so that they can join other reactions. Now, some are going to have a very low activation energy. They're going to really want to do this. Think a combustion reaction. But others are going to have a higher activation energy. And all that enzymes are trying to accomplish is to lower this activation energy. So here, this black line is without an enzyme. So the hill or the mountain that you have to climb energetically is very steep. With an enzyme, however, it is much lower. With an enzyme, you still have to input some energy, but the amount of energy is going to be much less. And what that's going to allow is it's going to allow this reaction to occur much quicker, and then many more of the reactions. And the next really cool thing about enzymes used up. So they're sort of above the substrate and the product conversation. They're going to stick around. They're just going to do their task, which is a facilitator, and then they're going to stick around. They're not part of the reactants or the products. So this particular example, you have sucrose, which is 2 sort of single ring sugars, 1 glucose, 1 fructose. Sucrose is table sugar. And so you're going to have an enzyme, sucrase. If you recall, the ACE the word is completely evaporating from my mind right now. But the ACE at the end is going to, the suffix, there it is going to mean enzyme. like os means sugar and ace is going to mean enzyme. And so what sucrase is going to do is it's going to create an environment in that active site with those R groups that attract, because again, this is not a dehydration synthesis. I don't know why I wrote that. This is hydrolysis, right? The addition of water to break things apart. So this is a hydrolysis reaction. So the enzyme is going to attract the sucrose, attract water, and then use the water and bond and change shape, which I'll show you a GIF of, to break the sucrose into the corresponding fructose and glucose molecules. This reaction, again, would normally happen, but it would not happen at the rate or the quantity that we need it to happen in the body. When we're talking about what is actually happening in these reactions, so this right here is kind of showing the different types of enzymes. So you have 4. We're going to start with the orange molecule. That orange molecule, sorry, again, it's been a while. The orange molecule was breaking things down. This green molecule is building things up. So you can see it's facilitating whatever those purple molecules were with probably a water hydrolysis, bringing them together. So again, we'll start with the orange. It's going to be breaking one molecule into 2. This would be like sucrase. This here is clipping off different structures. So that looks like it's clipping off a complex sugar. This one is building together, and this one is building together. We're taking 2 substrates and we're forcing them together. Now, how is this actually happening chemically? So this is a zoom in of an enzyme. The active site has specific chemical structures based on those R groups that make it really attractive to whatever its particular substrates are. Again, specificity here matters. And then once the substrates come in, they can actually kind of bond and interact with the enzyme, which is part of that lowering of the activation energy. So not only does the enzyme bring in and attract the things that are needed substrate-wise, but the molecules can actually then kind of bond to those R groups. That will change the shape of the overall protein just slightly so that it can do its job. So whether that's breaking it apart or putting things together. So because this is something else to think about, when the substrates come in and the enzyme is actively doing this, the shape is changed. So it can only do it one at a time. However, it is doing this incredibly, incredibly rapidly, faster than we can like probably fully comprehend in that regard. So this is a really cool image of this process happening where the enzyme, which is all those folded shapes around, the green is actively sort of allowing the molecules to interact and the reaction to occur. The last bit that we have here that's quite important, this is just the same sort of image, is that once that reaction has occurred, the enzyme sticks around. So what this is showing here is that you have substrates entering. The enzyme is going to do its shape change and facilitate that reaction, whatever it is. The products are expelled. Might be one product, might be multiple, but the enzyme is conserved. What do we mean by conserved? We mean that it's to stick around at the end and it can do it again. It's conserved throughout the process, so it's not going anywhere. That said, enzymes, though they are really cool, are not void of their own particular environments. So let's go back and let's think about what the chemical structure of the enzyme is. Remember, it's all chemistry, macromolecules. It has whatever its specific R groups are, is going to give it whatever its shape is. Well, those R groups and that shape and that series of amino acids is going to be highly specific for environments. So let's take, for example, an enzyme that you would find in your stomach versus an enzyme that you would find in, say, your blood. What is fundamentally different about those two things? The environment. Your stomach is highly acidic, and your blood, I believe, is slightly, ever so slightly basic, if I'm not mistaken, but it's much closer to neutral. So what's going to happen is if you were to swap those two enzymes, if you were to put the enzyme for your stomach into your blood and the enzyme for your blood into your stomach, what would happen? Well, the R groups of that particular amino acid. So if we go back to that very first image, this image here, these amino acids are bonded to their way. You put them in an environment that they absolutely are not made for. The environment will start to have chemical reactions with the actual enzyme and what we call denature it. And so it'll break apart. Important to think about, what do we know about structure? Structure dictates function. So if we start changing the structure because of the environment that the enzyme is in, it will no longer be able to do the function that it's supposed to do. So going back to the note sheets here, we have two different, these are sort of the main things that we think about when we talk about enzyme environment. The first is going to be temperature. And the second, oh, sorry, this is not where it should be though. The first is going to be temperature, and the second is going to be pH. So if this is a pH of 1 and this is a pH of, say, 14, I'm not sure what the book has, 1 and 100, or 0 and 100, this is the rate of reaction on the y-axis. And what should become very, very clear to you is that enzymes have different temperature affinities and they have different pH affinities. For example, if we look down here, this is a pH of 3. Sorry, I'm writing in highlighter now, apparently. This is a pH of 3. So in your head, you should be saying, well, this is an enzyme that really likes an acidic environment. This is probably a stomach enzyme, or an enzyme in like elsewhere in the world that really likes a very acidic environment. This, on the other hand, is an enzyme that has a strong affinity for a base environment, a basic environment. What you can see is that it's not like it's only going to work at this particular pH. There is a range. How big that range is depends on the enzyme itself, but that range is not going to be huge. It is certainly not going to span all of the pH or all of the temperature because of the R groups and the folding there. Temperature tends to be a little bit different, and that's because temperature correlated to energy. High temperatures typically are going to be pretty bad for enzymes, but there are quite a number of exceptions. So think about your human body, for example. What is the temperature there? Well, guess what? Most of the enzymes in your body are gonna thrive in that temperature because evolution has essentially selected for that particular enzyme amino acid series that forms that particular enzyme. If you're talking about like hydrosulfuric vents in the bottom of the ocean, that's going to be a different sort of temperature. And if you're talking about enzymes that are working in the Arctic, that's going to be a different temperature. So temperature, oftentimes we think about temperature being completely negative for enzymes, but it's within a range. So for example, if I take an egg, which has a lot of proteins, and I put it on a frying pan and I add a bunch of heat, I'm going to fundamentally change the properties of those proteins and denature them. The same can happen within the human body. This is one of the reasons why fevers are so dangerous for us as humans, right? Where there's a range where if we get to a certain temperature, we need to seek medical attention. Why is that? Well, it's because all of our proteins, not just our enzymes, but our other proteins are evolutionarily sort of built or selected for this particular condition. And if it gets too much outside of our homeostasis, our range for temperature, the proteins can begin to denature. And once those proteins begin to denature, they stop doing the functions that they are meant to do. Hope this helps. Have a good one. Fingers crossed, the third time's a charm. See you later, team.